This is part one of chapter one of exercise physiology. This chapter is going to give us an introduction to SI units and some of the calculations we might typically do in the context of assessment of exercise and work and power particularly. So here's a little list of topics we'll be kind of surveying as we go through this chapter. So the metric system is what scientists use when recording data to make calculations, and so we'll be sticking with the metric system and specifically the International System of Units. Those are just some standard units so that everybody's on the same page when we're talking about exercise and about the calculations we do. Here are some prefixes that I'm sure that you've seen many times, but just to keep things straight, they're just listed out here in terms of their meaning, and we will use only a very small subset of these. We might talk about millimeters and kilometers, for example, and that's about all we're going to encounter from this list. The SI units are important, though. The SI units include mass, distance, time, and volume, and then from those units are derived some additional units that will become very useful for us. So in terms of mass, we will use the kilogram. So whenever we're looking at our body weights, we'll always be converting them from pounds to kilograms. Distance in meters, and time in seconds. From those units, we can calculate newtons, and newton is a standardized unit of force calculated from these units. There's a standardized unit of work, which is the joule. It's an energy unit. Work is energy. Power is energy per unit time, the watt, and we'll take a look at that, and speed, meters per second. Those are the main units that we're probably going to use, mainly these SI units and these derived units. So let's define work. Work is the output of an exercise event. It's what amount of energy is imparted directly to some system, such as lifting a weight against the force of gravity. So work is an energy unit in joules and is defined as force times distance. And we'll stick with the SI derived unit of force, newtons, and distance in meters. So if we have a 10 kilogram weight, in order to figure out the work done when we lift it up against the force of gravity for 2 meters, we're going to need to convert kilograms into newtons. So here's a good number to keep in a list of shortcuts for yourself. 1 kilogram equals 9.181 newtons. And so now we'll just multiply and figure out that 10 kilograms equals 98 newtons. And then times the distance of 2 meters, force times distance gives us our work value, Newton meters, which is what we call joules. Here's some more ways of talking about expressing work in energy units. We see the joule down here, our unit we just defined, but just one more thing to add in here. When you see kilopons, you can just think kilograms. They're essentially, for our purposes, interchangeable. So don't be fooled if you see kilopon meters. That's the same as kilogram meters, and that is an energy unit. Kilocalories. Calories are another energy unit, and you can see a conversion right here, another conversion to put in your set of conversions or shortcuts for later use. 1 kilocalorie, 1,000 calories, remember that's the thousands prefix. 1 kilocalorie equals 4.19 kilojoules. That'll allow us to convert back and forth as needed. If you flip it the other way and do the inverse, 1 joule equals 2.39 times 10 to the minus 4th kilocalories. So we won't use that one as much, but it can be used as a way to convert. Power is work per unit time. How fast are you pumping out that energy? And so power, we just take the work value and divide by time in seconds. Joules per second is the power estimation or representation, I should say. But we're not going to leave it in joules per second. Oftentimes we're going to switch to a new unit called watts. So joules per second, 1 watt equals 1 joule per second. So that's always the unit that we're going to stick with. Here's an example of a power calculation. if there are 20,000 joules of work done in 1 minute, we're going to take that total amount of work, divide it by the number of seconds, because we want joules per second. We wind up with 333.3 watts. So our initial calculation gave us joules per second. We then equate that with watts. That's the unit we use. If we want to, in the laboratory or in the field, want to make some estimates, we need some kind of a device for measuring, usually in the laboratory, measuring work and power. An ergometer is a device used to be able to quantify work and power in some exercise bout. We're going to talk about bench stepping apparatus, and that's pretty straightforward. We call it an ergometer. That's a pretty highfalutin thing to call a step that we can step up and down on and lift our body weight against gravity. A cycle ergometer and a treadmill. Those are the ones we're going to take a look at. You probably won't take the time to look at an arm ergometer, although it's very, very effectively the same thing as a cycle ergometer in terms of how you do the calculations. So for a step ergometer or bench step bout of exercise, we can figure out the work by looking at the amount of weight that we're going to lift in newtons and how far we're going to lift it against the force of gravity in meters, and then how many times we're going to do that. So here we see in this example, we have 70 kilograms of weight. We're going to convert that to newtons because every kilogram is 9.81 newtons. So now we know that we have 686.7 newtons that we're lifting each time. And we're going to lift that for a distance of 0.3 meters times 30 times, or 30 steps per minute for 10 minutes. So we're going to add up to 300. And the total number of meters, when we multiply that out, that we're going to lift is 90 meters. Again, 0.3 meters per step, 30 steps per minute times 10 minutes. So now we wind up with 61,800 joules, and we're just going to use that familiar prefix thousands, kilo, to make it more of an accessible number, 61.8 kilojoules. Power, just joules per second, divided by the total time that we're talking about, 600 seconds, right? We wind up with 103 watts. 103 joules per second, 103 watts. For a cycle ergometer, it's a very similar kind of a calculation. We're just going to make the assumption or the estimate that every time the wheel spins on the cycle ergometer, that represents 6 meters of travel. That gives us our distance value, and we can convert from revolutions per minute to meters per minute, and then however many minutes we work for. So we have the resistance on the wheel is 1.5 kilograms, which is 14.7 newtons. We have 6 meters times per revolution. That's our standard value from now on whenever we're talking about cycle ergometry. In this case, we're working at 60 RPMs, or 60 revolutions per minute. And we're going to do that for 10 minutes, and you multiply that all together, and we wind up with 52.9 kilojoules. If we want power, we simply divide by the time. We have 600 seconds total time, right? And then so we take our 52,290 joules divided by 600 and get 88.2 watts. Treadmill runs us into a little bit of a problem because there's no distance that we're lifting the weight of the subject against unless we put a grade, an incline on the treadmill. So there's no easy way for us to directly calculate the energy of work when we're using a treadmill unless it's at an angle. So we're going to do that. We're going to use percent grade, and we're going to be able to calculate the vertical rise. That's how much the distance across which we're lifting the body weight. The vertical rise per 100 units of belt movement. So if we have a 10% grade, that's how you set the treadmill, we'll have a 10-meter rise for every 100 meters of travel, because 10% of that distance. That's what a 10% grade means. Right? So there's our little diagram of our 10% grade. You can actually do trigonometry to figure out the relationship, but we're going to stick with something simple here. So here we have a 60 kilogram person, which when we multiply that times 9.81, we wind up with 588.6 newtons. and the person is on the treadmill with a 7.5% grade. So now what is the work being done? It's the body weight. We have to figure out the total vertical distance. The vertical displacement means the vertical distance that the body is being lifted. So we take the percent grade, which is 0.075. That's how you represent 7.5% in a calculation. You move the decimal place two times for 2 powers of 10, because percent means per 100. So percent stands for. So we got 200 meters per minute times 0.07.5, the percent grade, times 10 minutes, and we now know that 150 meters of vertical rise is the total distance lifted, and the force, of course, as we said, is 588.6 newtons. So 588.6 newtons times that total vertical rise or lift gives us 88.3 kilojoules. So we're just using a little trick to give us something to go on in terms of the work done during treadmill running and walking. So that's just some quick ways we can figure out work and power using 3 kinds of ergometers. There's another thing to be thinking about when you're thinking about exercise and quantifying or assessing exercise, and that is, what about the total amount of energy the body has to invest to do that exercise? So these simple calculations, we came up with some work that was done, but that doesn't tell us the total amount of work the body had to do. What about all the breathing and all the accessory muscles and balancing and posture and the heart pumping and everything else the body is doing during the exercise? That goes into this question of energy expenditure, the true amount of energy used by the body to do the exercise. So how are we going to figure that out? We have to have a way to figure out energy expenditure, as ATPs, those are those chemical energies stored in the cell, is converted to ADP plus inorganic phosphate during the process of muscle contraction and all the other processes in the body. Every time an ATP is used, 2/3 of the energy is released as heat. So if we know the amount of heat release, that kind of gives us a handle on the total amount of energy that the body consumed during a particular physiological event, some sort of activity. So that means that if we could measure that heat release, we could work back and figure out the total amount of energy consumed by the body, because we know that 2/3 is released as heat. It's not that easy of a thing to do. We want to measure heat. How are we going to do that? We want to measure heat, which is a measure of heat as energy as calories or kilocalories. We're basically assuming that as food is oxidized to make ATP, as heat is released, and then as ATP is used for activities, heat is released. And so if we could measure that heat, we could get a total. We could figure out the total amount of work that the body did. How are we going to do that? One way that you actually can do that, and bigger programs may actually have such a thing as a direct calorimeter. A direct calorimetry is the actual measurement of the heat produced by the body and released from the body per unit of time. So if you just sit in a calorimeter, what's going to happen is heat is going to be radiated from your body and released from your body, and inside the calorimeter is a double wall with some water in between, and as the heat is released from your body, it's going to heat up the water in between those two jackets. And if you can very, very sensitively measure the change in temperature of the water, you can calculate the heat released from the body. And so also, if you're not just sitting there, that would allow you to measure the resting energy consumption of your body. And then if you did some exercise, you could theoretically stay in the calorimeter and measure the heat released. So having a calorimeter is not a very practical solution. Not too many college programs have a calorimeter for making direct calorimetry measurements. So in the next section, we're going to take a look at a method for measuring or estimating energy consumption or energy cost or energy utilization of the body by an indirect method. So that's what we'll be looking at next.